Hello, this is Dr. Muhammad, and this is a new video under the Seismic Design of Structures course. And still we are talking about the ASCE-7 seismic provisions. And today I'm going to talk about the amplification of accidental torsion with example. So we're going to talk about the torsion in general, and I'm going to talk about three different parts of it, which is already detailed in the in ASCE-7, and I'm going to talk about the inherent torsion and the accidental torsion and amplification of accidental torsion. These are the main three contents of today's lecture or video, and after that I'm going to make an application using an example. So I hope that you can understand more about torsion through this video. So now let's talk now about the code provisions regarding torsion. Whenever I mention about code here, I'm talking about, of course, ASCE-7. Actually, we are sometimes I alternate between ASCE-7, 16 or 10, because the latest version now we have 16. So in this video, I'm going to always refer to 16, ASCE-7, 16. And maybe in some particular places, whenever that I'm explaining, I'm going to indicate to ASCE-7 10. Actually, they are almost identical, except for some particular issues. I'm going to explain about them, but in general, they are the same. Whenever there is a difference or a big difference, I'm going to mention the difference. Okay, let's talk about the inherent torsion in the beginning, and actually it's an introduction for the inherent torsion. As we know that torsional displacement means that the twisting about the vertical axis occurs if the centers of mass, stiffness and mass of each story are not perfectly coincident in plan. Whenever that we have any kind of structure that is the elevation of the structure like this, and we have a plan, for example, something like this, and we have like different types of lateral resisting systems, sometimes that we can find there is a difference between two main points here. The first one is the center of mass, where that the forces of the earthquake are striking, or we are assuming that the force is coming here, and the center of rigidity. We call it CR, or the center of rigidity, where that the center of rigidity of all the resisting system in the plan, which are the columns or shear walls or whatever, are having one point considered to be a representative of the rigidity of the total floor. So if there is this kind of eccentricity, we say that there is torsion there, and we call it inherent. Means that it is already, it's natural, something that default. Okay, so this is the difference between the center of stiffness and center of mass, or center of rigidity, center of mass, or center. We call this center of stiffness or center of rigidity. They are synonyms. When three-dimensional analysis is used, this inherent torsion is included automatically. So if you are using 3D analysis, then already this inherent torsion is going to be there, because you have modeled all the elements accurately, and any kind of inherent torsion will be taken or will be considered automatically by default. However, whenever that you are making planar analysis, the centers of mass and rigidity for each story must be determined explicitly. You need to work out the places of the center of mass and center of rigidity, and you need to find whether that there is eccentricity there or not, and you are going to explicitly calculate it. Actually, in FEMA's P7 750, they are talking about this issue, and they said that it's difficult to determine the center of rigidity for a multi-story building to compute the inherent torsion. So the center of rigidity for a particular story depends on the configuration of the seismic force resisting elements above and below that story, and maybe load dependent. So actually this is some important hint that we need to highlight. as we said that whenever we are talking about the code provisions, they are putting some simplifications and they are making it easy for the designer or for the engineer to work out whatever the issue, whether that's torsion or drift or whatever. But we found that we need to understand that there is something like the most accurate level or the most accurate way of understanding the issue is that whenever that we have a floor and this floor is having, this is a floor and we have like different lateral resisting system at the left and right, for example, if we are talking about plan, something like this, and we have shear wall here and another shear wall here. Sometimes we can notice that for the same floor, we have like thicker shear wall beneath the floor, however that it is a little bit thinner above the floor. So whenever we are talking about this, we are going to find that it's a little bit not easy and difficult actually. It's going to be difficult for us to deal with such kind of irregularity or with such kind of change in the rigidity below and above the floor. And they also said that something that is very important, also it is mentioned in Chopra and Goel research in 1991, it is load dependent. It means that also it depends on the load that is applied on each floor. So we are in an approximation, in a way for approximating and making it simple. The code is going to give the next provisions that I'm going to explain, but we need to keep in our mind that it is really difficult. Okay, it is difficult to determine the center of rigidity for a multi-story building. Okay, we need to take into consideration the rigidity below and above, and also there is load. As we said, it is load dependent, so we need to think about this and keep it in our minds. However, the code is making it easy for us. So let's see how the code is dealing with this issue. Under section 12.8.4.1 inherent torsion, the code is stating that for diaphragms that are not flexible. What is the meaning of this? Means that we are talking about rigid diaphragm. Okay, rigid diaphragm. What is the definition of rigid diaphragm? We're going to talk about it later, and you're going to find one section in the code talking about the rigid diaphragm. So if we are talking about a case where that the diaphragm is rigid or it is not flexible, the distribution of lateral forces at each level shall consider the effect of the inherent torsion moment, MT, we call it M with the subscript T, resulting from eccentricity between locations of the center of mass and the center of rigidity. This is clear and we understood it well. For flexible diaphragms, the distribution of forces to the vertical elements shall account for the position and distribution of the masses supported. So what is the meaning here? What I want you to understand from this paragraph, that we need to differentiate between two different levels of the diaphragm, whether it is flexible diaphragm or rigid diaphragm. Okay? Because if it's rigid diaphragm, then what I'm going to explain from now on, it is applied on the rigid diaphragm. Rigid diaphragm means that the floor itself, if we have the floor, okay, the floor itself, it fulfills the condition of a rigid diaphragm, and all the floor is able to transmit and transfer the lateral force based on the rigidity of the elements of the lateral resisting system, based on their rigidity. Okay, so the diaphragm is rigid enough. So now we are going to talk about this issue, but the code is highlighting something that is important. If there is flexible diaphragm, then the whole understanding of the torsion will not, our understanding and the simplification will not work for us, and we need to use the tributary area for putting the forces on each element. So for example, if we have something like this, let me draw something like a little bit bigger, and we have columns, for example, here and there, and we have like shear walls here and another shear wall here and so on. The point is, if this diaphragm, which is the floor, it is flexible, we are not going to assume that the force is coming on the center of mass. If we have center of mass and center of rigidity, if we have Cm here and we have center of rigidity here, and the force of the earthquake is coming or applied on the center of mass, we are not going to assume that this force is going to be distributed among the lateral resisting systems using the concept of rigid diaphragm. It will not work like this. What we are going to do is we are going to look to each element and see what is the tributary area, which is something like this, for example. And for this wall, it will be something like this. And for this column, it will be something like this. These are the limits. And based on these limits, we're going to multiply the mass times the acceleration and say that this is the portion of the force that is going to be resisted by this element. Okay? So this is the case for flexible diaphragm, the way. This is why the code is doing it or putting it very straightforward here. For flexible diaphragms, the distribution of forces to the vertical elements shall account for the position, that's here, like as I said, the position, and distribution of masses supported, the tributary area. Okay? But from now on, I'm going to talk about the rigid diaphragm, which is our main concern. Okay? Because in most cases, in most buildings, we are facing like rigid concrete floor or composite floor, for example, like steel and some studs and some steel and like a cover concrete with 5 centimeters or so or higher or 10 or something. So both, they are considered to be rigid in most cases, but in many cases also we can find the flexible diaphragm. And this is, we can put it like this, for buildings with fully flexible diaphragms as defined in this section. So the definition, you can find it in 12.3. Vertical elements are assumed to resist inertial forces from mass that is tributary. This is the key word here, to the elements, but with no explicitly computed torsion. That's very important, and it concludes what I have explained right now. No diaphragm is perfectly flexible, and this is another point here. We cannot assume that any diaphragm to be 100% flexible. So some torsional forces always develop, even when they are ignored. Okay, so keep in your mind that even that we said this diaphragm is flexible, but there is some rigidity there, and there might be some torsional would be there, but maybe it is ignored, as we said. This is from FEMA P750. Okay, let's go now to the next point, which is the accidental torsion. In the accidental torsion, what we want to highlight here is that when there is a rigid diaphragm and when there is inherent torsion, we need to check for the structure. We need to check for the structure. And if we have planned something like this, if there is kind of distributed different resisting elements, as we can see, for example, here, if there is inherent torsion, okay, we need to add some accidental torsion. Okay, so we need to add accidental torsion. If we have the center of mass and center of rigidity, they are, as we said, they have eccentricity here, inherent eccentricity, inherent torsion is there. They are not coinciding on one another. Then there is something that we are fearing from, which is there might be a rotational component of the earthquake ground excitation. There might be something like this. Or our accuracy for putting the center of mass and center of rigidity, the position of center of mass and center of rigidity may be not accurate. So we need to take some accidental torsion into consideration in our calculation. So accidental torsion accounts for rotational effect of the earthquake and the difference between the actual and computed stiffness, strengths, and masses, which is some error between the computed and the actual. Even for perfectly symmetric buildings, the true locations of the centers of mass and rigidity are uncertain. That's very clear for us. So this is why we need to take the accidental torsion into consideration. Okay. And whenever that we are going to have, if we assume that the center of mass and center of rigidity, they are coincide on one another, if there is no inherent torsion, then we're going to assume that the force is going to be whether having eccentricity like 5% to the right or 5% to the left. We are going to check this alone, we're going to check this alone, or the third case is if there is no accidental torsion at all. We are going to check three cases, okay, for the elements. All components of the structure must be designed for the maximum effects considering positive accidental torsion, negative accidental torsion, and no accidental torsion. Maybe it is a little bit counterintuitive for you to think about no accidental torsion. What is the point in this? You're going to see in the example that some cases maybe no accidental torsion would provide some additional forces on the lateral force resisting systems compared to the case 1 or case 2. We're going to see this in the example. Okay. Now let's read what the ASCE-7 is telling us about the accidental torsion, where diaphragms are not flexible. Look to this point. Always the code is placing emphasis upon it because it's important. Not flexible. The design shall include the inherent torsion moment MT resulting from the location of the structure plus. This means plus means that in positive or in negative and two directions. Okay, as I said, this is okay. This is plus here or minus. If we have like this is the center of mass. We are going to put additional eccentricity or accidental torsional, okay, by putting it as I said, like to the right and to the left of the center of mass. The accidental torsion moments MTA caused by assumed displacement of the center of mass each way from, look to this word, each way from its actual location by a distance equal to 5% of the dimension of the structure perpendicular to the direction of the applied forces, which is we are talking about this case. If we are having our earthquake load here, then we are going to talk about 5% from this L. Okay, 5% of the length perpendicular to the force applied. Where earthquake forces are applied concurrently in two orthogonal directions, the required 5% displacement of the center of mass need not to be applied in both of the orthogonal directions at the same time, but shall be applied in the direction that produces the greater effect. Okay, he is talking here, let me clear this. He's talking here about the case where that we need to analyze for two cases, perpendicular cases. So in this case, sometimes we put like 100% of the earthquake here and 30% of the earthquake here. Then he is talking here that if we're going to put and apply accidental torsion, we are going to apply the eccentricity in the position where that it makes the greater effect. Okay, the greater effect. So we are going, actually we need to check them, both of them, because maybe if we are going to make some eccentricity for 100% and check, for example, for one column here, maybe if we apply the 30% with the eccentricity in this direction, maybe it will give more loads or more stresses on this element. Okay, so this is why he's telling that in two orthogonal direction, the required 5% displacement of the center of mass need not to be applied in both of the orthogonal direction at the same time. So we're not going to apply like 5% here and 5% here. It's not allowed. I mean that it's not required here. Okay, but in the same time, but shall be applied in the direction that produces the greatest effect, and this needs investigation. Accidental torsion shall be applied to all structures for determination if a horizontal irregularity exists as specified in this section. Another case where that, or another point that need to be applied, if we have torsional irregularity. Torsional irregularity is, I'm going to show you the table. This is the table 12.3-1, horizontal structure irregularity. We're going to find type 1A and type 1B. This is torsional irregularity and this is extreme torsional irregularity. So in these two cases, if we encounter a building that is having one of these cases, okay, then we need to apply accidental torsion. Okay, we need to apply accidental torsion. This is what it is. Accidental torsion shall be applied to all structures for determination if a horizontal irregularity exists, and as specified in this table that I have shown to you, accidental torsion moments, MTA, need not to be included when determining the seismic force E in design of structure and in the determination of design story drift. Okay, section, these sections, or chapter 16, or limits of section, except for the following. Actually, these sections, they are dealing with some specific cases. The most important one from my own point of view is the story drift. Okay? For story drift calculation, we're not going to take into consideration this torsional amplification. Okay, this is what they are telling here, or determining the seismic forces E based on these sections. You are going to find that there is some exception here, exception 1 and 2. One, it is for seismic category B with type 1B horizontal structure irregularity. This is the extreme case of torsional irregularity. And for other seismic categories, except B, for example, for the two, of course, and with type 1A and type 1B for both cases of structural horizontal structural irregularity. Okay, so actually our case, we are not going to go into the details of this because it is exceptions. We need to follow everyone, but my main concern is the accidental torsion and when not to use it. Now let's go to the last part, which is the amplification of accidental torsion. So we are going to amplify this accidental torsion as well. So this equation, which is equation 12.8-4, you are going to find it under this section in ASCE. It tells us that there is an amplification factor that is going to be used. And this amplification factor is going to amplify the accidental torsion. So the accidental torsion that we have explained in the previous slide, it needs to be amplified. Okay, so these are structures assigned to seismic design category C, D, E, or F with type 1A or 1B torsional irregularity exists. So this is the case here. If we have torsional irregularity with 1A or 1B, in this case we need to apply the amplification of the accidental torsion. Okay, shall have the effects accounted for by multiplying MTA. This is the accidental torsion going to be multiplied by this factor, which is AX. Okay, AX, the amplification factor. And this would be done for at each level by a torsional amplification factor, AX, as illustrated in this figure. You're going to find this. This is the figure here. So if we have the average, okay, the condition here that, if you remember that we said that for the torsional irregularity or for horizontal irregularity, we have delta A and delta B over 2, where delta A, it is the edges inelastic displacements, the average of them. If this average is larger than, or the maximum one of them is larger than, if delta maximum is larger than 1.2, this delta average, then we are under 1A horizontal irregularity. And if this is 1.4, then we are under 1B horizontal irregularity. Okay, so based on this, as you can find from the table here, this is 1.2 times the average. Okay, and for the extreme it is 1.4 times the average. Okay, so this is 1A and 1B. So whenever that we are having these kind of irregularities, in this case we are going to amplify the accidental torsion by this factor, which is going to be delta maximum over 1.2 delta average to the power 2. Okay, where delta maximum, it is the maximum displacement at level X computed assuming that no kind of amplification factor, and delta average, it is the average displacement of the extreme points of the structure at level X. We are talking about levels here. Okay, it is, we should calculate it for each level and each floor. Okay, so this is an important issue. And we found that also this factor need not to exceed, it should not exceed 3. Okay, and it should not be less than 1, of course. We are amplifying, so it should not be less than 1 and it should not exceed 3. Okay, the more severe loading for each element shall be considered for design. Because we are applying it in each direction, so we are going to find that there is kind of different cases that we need to check, as we are going to see in the example. Let me summarize what I have said. This equation, which is 12.8-14, was developed by SEC, the Seismology Committee, to encourage building with good torsional stiffness. So that's the point. This is the main concern. If you're going to ask why we are making amplification here further and so on, why we should not go with the inherent and accidental torsion, it's enough for us. Actually, this is like historical kind of ruling or provision, that is to encourage the good torsional stiffness. If you are going to be within type 1A or type B, this is not recommended. So they are like putting penalty upon you by adding more amplification on the accidental torsion. But if you keep your structure that is not having these type of irregularity, then you are not going to find this amplification factors needed. Okay? Okay. In calculating the torsional amplification factor, AX, the applied loads include inherent and accidental. That's very important. This delta maximum and this delta average should be calculated taking into consideration the inherent, which is MT, okay, plus MTA. Both of them should be used in order to obtain these delta maximum, delta average. Okay? But with no further amplification, you're not going to amplify more, because we're going to be into a loop. That is, every time we put MT plus MTA and this MTA is going to be amplified, then we're going to do it again and over. This is not required. Only one time. Okay, it is not iterative. Take care of this. Okay, now let's go to, I think we are ready now for the example. Okay, so we have an understanding now of what is the meaning of inherent torsion, as we have explained it, and after that we mentioned about the accidental torsion and what is the understanding and the rationale behind it, and we said that we need to check these 3 different cases. And after that, in order to put some penalty for structure type horizontal irregularity 1A and 1B, we are going to apply a kind of amplification factor on the accidental torsion. We said that it is historical provision in order to improve or to encourage building with good torsional stiffness. And we mentioned that the inherent and accidental torsion should be used for the calculation of the components of this amplification factor. Okay, now we are ready now to take the example, which is going to be shown. This example from the Seismic Design Manual 2012, and it is using 2010, which is ASCE-710. Okay, so that's it. But again, almost the identical with ASCE-7-16. Okay, now we are going to talk about this, the amplification of accidental torsion. This is the provision that you can find it in the table as we have explained. Let's look to the problem statement. So the structure shown here is a 5-story reinforced concrete building. It is reinforced concrete building, RC building, frame system. A 3-dimensional rigid diaphragm model has been formulated for the evaluation of the element actions and deformations. So actually, as usual in our daily routine for offices and so on, we are like making the 3D model for this structure, and we have obtained the actions and deformations due to prescribed loading conditions, which is already we have explained in the previous videos. Shear walls resist lateral forces in both directions. If you look here, you're going to find that shear walls here, as it is indicated here, A, and another shear wall here, which is B. And our direction for the earthquake, it is here, which is north-south direction. And in the perpendicular direction, which is not going to be considered in our example, also we have these shear walls also. Okay. The center of mass of the position of the applied forces from the earthquake is going to be on the center of mass, CMX, we call it. And as you're going to see, it is coinciding on the center of rigidity, assuming that the center of mass is in the same position of the center of rigidity. Okay. Okay, so all the actions should be given for us, as you are going to see here. The lateral seismic force, Fx, which as we said, it is this Fx, in the north-south direction, and the structure dimensions and the accidental eccentricity for each level are given below. So we have here the level, which is the story. We said it's 5 stories, so we're starting from 1, 2 until 5. And the Fx, it is the lateral force, which is already, we can obtain it from the analysis. Okay, these forces are, as you can see, it is 23 here and ending up with 110 at the top. Lx, it is the dimension perpendicular to these forces. As you can see here, this is 80 because we are talking about this direction. So it is 80 for all of them. It is for all floors. We're talking about the maximum one, okay? The maximum perpendicular length, not this one. And x bar cs, it is this x bar cs, which is the distance of the force applied on the floor from the center of shear wall A. That's the point here. This is the meaning of x. Okay, so we have this is like 32 in the first floor, 30 in the second. They are different. It seems that the center of mass of each floor is different from this edge, from like this axis, x1 for example. It seems that this center of mass is moving right and left for each floor. They are not the same. For example, first floor it is at 31, let's assume it is here, but for the 5th floor it is 24. So the center of mass is going to be here, for example, for the 5th floor. So each floor should be studied alone in order to obtain the center of mass. And then, of course, we are going to put the eccentricity, which is accidental eccentricity, which is 0.05 of the length here, which is 0.05 times Lx, and we have it 4. All of them, they are 4, because Lx, it is fixed 80. 0.05 times 80, it is 4 foot. And take care that it is plus or minus. We are going, as we said, we're going to apply the force, the center of mass. So we are going to say that there is like plus eccentricity or there is minus eccentricity. Okay. So this is the significance of plus and minus here. Okay, now let's go to the next. And now we have obtained all the dimensions, but we need to know the straining actions at the shear walls, which is shear wall A and shear wall B. We want to know the straining actions for the cases where that the force is applied on the center of mass, which is x bar here, means that the center of mass, or x bar minus the eccentricity, or x bar plus the eccentricity. So it seems like we are talking about 3 cases now. This is the center of mass where there is no accidental torsion is applied or eccentricity is applied, and then we are going to apply, this is the position of this force, which is x bar here, and other point which is plus eccentricity, which is this one, and other point which is minus eccentricity. Okay, so we have, this is E, and this is another E. This is positive and this is negative. So we have the force is going to be, we are going to check the forces in three different places. This is Fx, this is the same Fx also, and this is Fx, but they are different cases. So the first case, when we apply Fx at the center of mass here without any kind of eccentricity, these are the information provided. So for example, the wall shear VA, which is the shear at this wall A, it was found 185. Okay. However, if we apply the Fx with negative eccentricity, which is negative here, we found that this force is going to be increased. It is 196, right? Because we applied it here. And this is logic, actually. When we put Fx a little bit here to the left, shifted to the left, the amount of shear that is going to be carried by A, it is larger than the case when Fx is here, right? So we are expecting this 196. However, if we put the force to be here, we're expecting that the force to be less than the original case, right? So if we are talking about this wall, which is wall A here, and we have this is the original case, which is 185. This case is going to be 196, the force here, but here the force here, or the shear force here, is going to be 174. In a similar fashion, we are going to follow for VB here. It is the forces in each case, okay? In a similar fashion also, we're going to find that 115 here. However, that if it's positive, you're going to find that it's larger because B is here, right? So Fx, the positive, is going to be 126, that's right, bigger than 115. And the other one, which is negative, it is going negative E accidental, it is going to be 104. So this is logic, actually. It flows in a logical way. And story drifts, take care of the story drift. This is also calculated here, which is the story drift means that the difference between the absolute, so if we have this is the top floor, okay, and this is the bottom floor. So if we say that it was here, for example, okay, the structure was here. So this movement here, this is the difference between the two. It is considered to be delta, okay? This is considered to be delta, the drift, okay? The drift. So the drift here, this delta, it is going to be delta 1 for this floor, which is floor 1, for example. If this floor, it is related to the ground, for example, here, so, and it is like, was moving like this, so this delta should be delta node, or the original, or the first. If we say, for example, this is first floor, this is second floor, so this delta should be second floor, this delta is first floor. Okay, so now this is the meaning of the drift. But the absolute displacement, which is delta A and delta B, it is totally different. I'm going to show you the difference between the two. Let me show you something here. Yes, something like this here. So this is the difference actually between delta 1, this is the absolute inelastic displacement. However, delta 1 and delta 2 here, it is the difference between the two. So delta 1, this is 0 here, and we have some movement here, so this is delta 1. However, this one, which is the difference between the two, this is the ultimate point here of floor 2, this is the ultimate point of floor 1 after inelastic. The difference between the two, it is delta 2. Okay, so this is the difference between the small delta and the big delta. Okay, this is the drift, this is the absolute displacement. Okay, now let's go back again to our case. Okay, so we have everything now for the information for the shear and the story drift and the absolute displacement. We're going to use all of them here. Okay, now let's go and see what should we determine. So we need like 4 requirements. The first one is, what is the maximum force in shear walls A and B for the second story? So we're talking about the second story now, and we want to know what is the maximum shear at A and B. Another requirement is we want to check if there is torsional irregularity exists for the second floor. We need to check it. It is going to be checked using the drifts, as we said, or yes, this is going to be based on the drifts of each floor. And requirement 3, amplification factor AX for the second story, and for new accidental torsion eccentricity for the second story. These are the 4 main requirements. So let's go and see how we are going to solve for the first one. The first one, it is what is the maximum force in wall A and B for the second story. From the table, if you look to the table, you're going to find that we want the maximum. So we're going to look to shear in wall A and wall B, and we have 3 cases here. Okay, 3 cases. So now for wall A, from these 3, we're going to get the maximum, okay, which is 196, and this is true. Okay, and for case B, we're going to check the maximum here, which is 126, which is this one. Okay, so this is the maximum. Take care here. For A, shear wall A, the maximum coming from applying the force with minus eccentricity. But for B, it is it is result of applying the force plus the eccentricity. And this is logic. This is logic, right? Because B on the right, wall B here, but wall A is here. So whenever that we shift the force to the right, means that plus eccentricity, then we are expecting B to have the force, the maximum force. And the opposite applies for A. Okay? Okay, now this is logic and we can obtain it easily. Okay, now let's go to the as we said before, we are assuming in our structure that the center of mass, CM and CR, they are coinciding on one another. Okay, in our example, we assume that there is no inherent torsion. Okay, there is no inherent torsion. So this means that we are from this table, it is okay for us. It is the maximum is going to be obtained using the accidental torsion that is applied. Okay, but there is no inherent torsion. Okay, now let's go to the second requirement, which is we want to check if torsional irregularity exists for the second story. Okay, for torsional irregularity, we need to recall what is the torsional irregularity actually here. Yes, from this table, table 12.3, we're going to find torsional irregularity means that if the drift, the maximum story drift, we're talking about drift, not delta, small, not absolute inelastic response. If this is the drift, okay, this drift computed including accidental torsion with AX equals 0, there is no amplification of the accidental torsion, only accidental torsion will be used. Then at one end of the structure transverse to an axis is more than 1.2 times the average. Okay, so this is actually, if we're going to put it here, yes, I have shown this before. Yes, here, this is the torsional irregularity. If this if we're going to talk about the maximum, okay, if we're going to talk about the drift here, we're going to talk about the drifts, the maximum, and we're going to talk about the delta average. So if delta maximum, okay, is larger than 1.2, then it is torsional irregularity 1A, but if it's larger than 1.4, this means that it is torsional irregularity 1B. Okay, this is what we have said here. Let me check this here. Yes. So delta maximum, the building may have torsional irregularity type 1A, and this is as I've shown to you in the table. The following is a check for this drift. What is the delta maximum? We will go to the table. So now we are going to check this. Okay, we're going to check that. What is the delta maximum? We're going to check the maximum delta for all cases, and the delta here we found that For minus eccentricity, it was 0.37 and 0.56. However, for plus eccentricity, it was 0.33 and 0.68. Which one that we should take? Actually, we need to check both because we should take the maximum one. If you going to take the average of these two, it seems, or it is, as you can see, it is less than the average of these two, right? So this average is less than this average. So this is the case where that, yes, this is the case where that might be susceptible to have maximum or to have the torsional irregularity. Okay, so here first of all we're going to check the maximum value, which is 0.68, which is this value. This is the maximum one. Okay, it is the maximum in all cases. So our structure is going to have 0.68, and the corresponding average is going to be, I think there is something here. This is the average of these two. So we check what is the maximum in all of them, and we'll find 0.68. Then we're going to check the average of them. Okay, because maybe we are going to check, for example, for this one, for this case, the average is going to be, the maximum is going to be 0.56, and the average is going to be this average, right? So we need to check whether that this average is going to be the maximum, or this average is going to be fulfilling the condition or not. But the code is telling us the maximum only. He's telling the maximum, so we should check the maximum, which is 0.68, and check the corresponding average of it. Okay, so that's what we have done here, 0.68. So forget about this. Okay, forget about this now, and let's go with the 0.68, which is the maximum, and the corresponding average is going to be 0.68 plus 0.33, both of them, over 2. This is 0.51, and the ratio between delta maximum over delta average, it is 0.68 over the average. It is 1.33, which is higher than 1.2. This qualifies it to horizontal irregularity number 1, so it is 1A. Okay. If it's larger than 1.4, then it will be 1B. But in our case, it is not 1.4 or not exceeding 1.4. It is only exceeding 1.2. Okay. Okay. So now this is the second check for us. Okay, for the horizontal torsional irregularity. Now let's go to the third one. It is determine the amplification factor AX. So in the amplification factor, we are going to use the absolute or the maximum inelastic displacement. So the last two rows of the table are going to be used. Okay. So now if you are going to look, okay, because the torsional irregularity exists, this section, which we already explained before, requires that the second story torsional moment be amplified by the following factor, which is this factor that I have explained. So we assume that in this example, the only source of torsion is the accidental torsion. There is no inherent torsion. So the amplification factor will be used to calculate a new and increased accidental eccentricity as shown below. So we're going to first get the amplification factor, which is AX. It would equal to, take care, delta maximum over delta average. We are using the displacement, inelastic displacement. Okay, it's not related to the drift. We are not talking about the drift here. So delta maximum in our case, it is going to be by investigation. You are going to find that delta maximum is, yes, 1.44. This is the maximum inelastic displacement. It will be, in this case, for shear wall A, for shear wall B, and under this case of eccentricity, the +1. Okay, the +1. If you look here, for example, this is the plus eccentricity, this is minus eccentricity, and this is without eccentricity. Look here to this value, 1.31. It is larger than this value, okay, for example. So if we're going to check only, if we're going to check minus eccentricity versus the no eccentricity will be the winner here, okay? So this is why we said that the maximum effects should consider three different cases. Positive accidental torsion, which is this one, and then negative accidental torsion, which is this one, and no accidental torsion, which is this one, okay? But here in our case, we found that positive accidental torsion was the winning case. It is the maximum here. So we found that it is 1.44. The average story displacement is computed. We are going to use the average here, okay? So it is going to be 1.44 plus 0.75, okay, from the average, okay, because as if that our structure is going to like move in this direction, okay, we're going to have something like this, okay, so as if that it is moving, for example, here, and this is here. The difference between the two, here it is higher. We say that the original was here, and here it was like in I'd like to show it here better. Yes, so if we're going to assume that, let's assume this is here in delta A and delta B, but actually it is flipped in our case. But if we have the structure to be deformed in this shape, so we are going to have this delta A here, and we are going to have delta B to be here, and then we are going to have the case for the torsion. Okay, so now we have this delta average 1.1. Then the amplification factor for the second story, 2 here stands for second floor. It would equal to 1.44, which is the maximum one, over 1.2. This is given in the already in the equation, and then times 1.1, which is the average that we have explained. It gives us 1.19. This means what? This means that we are going to amplify the accidental torsion and reanalyze the structure again. That's the meaning of this case. So here, this is only a reminder of what we have said before. So this is going to be based on the, as we said, the inelastic maximum displacement, and we are going to amplify. Take care, we are going to amplify where type 1A and 1B torsion irregularity exist as defined, shall have the effects accounted by multiplying MTA. Take care, we are going to multiply MTA, the accidental torsion, at each level by torsional amplification factor AX. Okay, this is what we are going to use now. So let's go here. So the accidental torsion is going to be 1.19 from the previous slide times 4, which is already the torsion that, if you remember in the first table that we have explained, we had 4 plus or minus, which is 0.05 Lx. Now this should be multiplied by 1.19. So it should be the new value for the second floor. It is going to be 4.76. Okay, so that's the case for our, this is the new accidental torsion eccentricity for the second story. It is 4.76, not 4. Okay, there are some comments I want to share with you. Okay, like a bunch of comments here. Example calculations were given for the second story, right? We were concentrating on the second story. However, in your design, which is in practice, each story requires an evaluation of the most severe element, actions, and a check for the torsional irregularity condition. This means that you need to check it for each floor. Okay, here only we were concentrating on the second floor for brevity, but actually you should check for every story or every level. The second comment is, if torsional irregularity exists and AX is greater than 1 at any level or levels, a second torsional analysis must be performed using the new accidental eccentricities, as we have done. Found that our 1.19 amplification factor needs to be done. However, it is not required to find the resulting new AX values and repeat the process a second or third time. Okay, so this is not required, means because you are going to amplify, if we go back, we are going to amplify, we are going to reanalyze again. Okay, and then no need for you to go again and calculate this AX. No need for this. It's only once. Okay, it's not repetitive. Only once. Okay. So the results of AX in this case, it will be sufficient for the design purposes. No need to iterate or no need to make more iterations. While this example involves wall shear evaluation, the same procedure applies to the determination of the most severe element actions for any other lateral force resisting system having rigid diaphragms. Again, we're talking about rigid diaphragms, not flexible, and you can apply the same procedure in any type of lateral force resisting system, okay, like braced frames or moment frames or anything. The last one is for dynamic analysis. So when the dynamic analysis method in section 12.9 is used, all the requirements of horizontal shear distribution given in the section 12.8.4, including torsional calculations that may accounted for by displacing the calculated center of mass of each level, okay, also apply. Means that you are going to apply the same sense, what we have explained before, you are going to apply it. However, section 12.9.5 states that amplification of accidental torsion is not required where accidental torsional effects are included in the dynamic analysis. That's it. If you are including accidental torsion in the dynamic analysis, no need to do what we have done. Okay. Also note that AX not required to exceed 3. AX is not required to exceed 3. So this means that if you are going to include it in your model in the dynamic analysis, so there is no need to make the analysis. Okay, for what we have explained before for the torsional and so on. And this is logic, I think. Okay, now this brings us to the end of this video. I hope that you have understood well what is the meaning of inherent torsion, accidental torsion, and amplification of the accidental torsion, and how we can apply it using the examples or the example that I have explained here. Thank you very much and see you in the next video.